Okay, I guess it's my turn to get going here. The music has stopped. So thank you for having me. My name is Remzi Arpaci-Dusseau. I'm a professor at the University of Wisconsin in Madison. And today I'm going to talk to you about some of the work that we've been doing in the storage domain for the past few years. So I'm going to actually give a little bit broader of a talk than I tend to do, but what I'll hope that you do, and I kind of plan on you doing, is where you see interest or where you see questions, please feel free, of course, to interrupt me as you see fit, and we can talk about things in more detail if it's so desired. So what I've titled my talk is Living in a Layered World, and let me talk about what I mean by that. Of course, we all know that systems are built from layers. Classic example, of course, comes from the networking domain, where you talk about applications built on sockets, built on TCP, IP, Ethernet layers. Each layer comprising some bit of functionality that we need to build end-to-end applications, say in a networked world. And layers are obviously a good thing for lots of reasons. They decrease complexity. You can focus on one part of the system, do that part well, increase modularity and so forth as well. You can put, for example, UDP on top of IP. And in storage has become, if you look historically at storage has also become increasingly layered. Years ago, we had a file system, and it actually, unbelievably, managed directly a bunch of disks. And the disks even exposed things like internal geometry to the file system themselves, and the file system had to manage it. A first kind of abstraction that we saw some years ago was a more abstract interface being positioned between the file system and the disk. So instead of geometry and low-level details, suddenly we had an abstract SCSI-like block interface between disks and the file system. Another layer of sorts, making the distance between the file system and the disk a little further. And we had RAID systems at some point, of course. Another layer which, again, hid and virtualized, another layer that did things between the file system and the disks. And then, today you could throw in a network, what have you, a virtualizing router even. You could go on, you know what types of things I'm talking about. Of course, layers, as well as being a good thing, also introduce numerous problems into systems. Of course, they can introduce performance problems, the typical kinds of things. But what I'm really going to focus on is the loss of information that layering often induces. And the hypothesis really hiding behind a great deal of our work is that this kind of layering and this loss of information that occurs because of that really prevents us from building many new and interesting kinds of systems. And I'll talk about that in more detail throughout my talk. And so what our research at Wisconsin has been a lot of dealing with how to build systems, interesting systems that deal with the fact that they're part of a layered world. And so how do you learn more about other layers that you're interacting with, and how do you exploit that to build more interesting systems? It's been a focus of ours. And I'll talk about that in more detail, of course, as well. So this is an outline for the rest of my talk. I'm not going to talk about any one thing in too much detail, though I'll spend a little bit more time up front on the first few things. And so what I'll start with is some work we've been doing at the kind of the bottom layer in this simple stack, a storage stack I've shown on the right, so in this RAID layer. And what that RAID layer is sitting underneath is underneath of a file system. So I'll talk first about some work in how do we get a block-based storage system like that, a RAID system, to learn more about the file system above it, what's going on in that file system that actually reading and writing blocks on top of the RAID. And I'll describe that through a few case studies and spend a great deal of time on one of those. Then after that, I'll look at another issue in storage layering, but from a top-down perspective. What if you're a file system sitting on top of a RAID box, and you don't know a lot about that RAID box? How can you learn more about it so that you can better tune your file system to work with that RAID? I'll then shift gears a little bit and just talk for a bit about some system analysis that we're doing. In fact, we're dealing with a product from a different company there, so you'll have to excuse me. But we've done some work with the EMC Centara, and we've developed some tools and techniques to analyze systems like that to figure out what they're actually doing. What are their internal policies? What are their communication protocols that they use? And in some ways revealing what they do in this great layered system. And then finally, what I'll touch on at the very end of the talk, and I won't spend much time on this at all, though I'm happy to talk to you about it at that point or afterwards. I'll talk about some new directions that we're thinking about right now, directions about handling failures, all types of disk failures that do occur, and some of the work we've been thinking about in virtual machine technology, which is really just yet another layer that's getting inserted in our storage system stack. So what I'll start off is with our work in that RAID layer. in block-based storage systems. And I'm going to talk a little bit of detail about this. So it's going to take me a while to get through this part. Don't worry, most of the rest of the talk actually goes very quickly. So I'll be spending a good deal of talk on this and then going more quickly through everything else. And what we started with was this basic observation. At a low layer in the storage system, when you're inside of a typical RAID box, let's say, that's a block-based RAID box sitting behind, say, a SCSI or fiber channel kind of interface, that block-based storage system doesn't really know a lot about how it's being used. It has some file system or a database above it, and it sees a bunch of reads and writes, but it doesn't have a lot of information as to what those reads and writes really mean. It's too dumb. It doesn't really know anything about how it's being used. And the reason, of course, as you all understand, is the problem with these kind of block-based storage systems is that the interface to them is so narrow, a SCSI-like interface, which really just says, I can read this block or I can write this block. But the storage system is left not being able to know simple things, which could be very useful. It might be very useful for a RAID storage array to know which blocks are alive or dead. It might be useful to know which blocks form a directory versus just user data, because we might treat those types of blocks differently. We don't typically know those things, though, inside of a RAID array, at least in this kind of layered world with, say, a SCSI interface between us. Now, we could change the interface, but we viewed that as an impractical, not a very pragmatic approach. Bill Joy once said that systems come and go, but protocols live forever. And the point really there was, it's very hard to get people to agree on a new interface, maybe a new interface that told you more about what the file system was doing. And you could almost view, for example, Seagate's been trying for almost 10 years to move to an object-based storage system, a slightly higher level interface that conveys more information. But it's quite an effort to get an industry to move towards a new interface when there's so much existing stuff out there. And so what we wanted to say is, well, what can we do? Would there be a way for us to build smarter storage systems that could learn more about how they're being used, but without changing the interface to storage? And so that's what I'll spend a little bit of time talking about today. It's a type of storage system which we call a semantically smart storage system or a semantically smart disk system. And that's a disk system that understands things about, say, the file system that's using it, its data structures, some of the operations that it does. Now, the key to any semantically smart disk, and we'll see this as we get into more detail, is that it has to operate underneath an unmodified file system and an unchanged interface. So we're somehow going to have to be able to do this without changing anything about the systems above the RAID, the file system, for example. And so somehow we have to discover things like how does the file system do layout and non-disk structures, static information like that, for example, where inodes are on disk. And then we also have to be able to take that plus the block stream that's currently updating the file system. For example, we might be getting new writes that are changing the state of the file system at a given point. We have to look at that too and pay attention to it and reverse engineer that into understanding really what the file system is trying to do. And I'll talk about all these things in more detail so you can get a flavor of what we're talking about there. So this is an outline for this part of the talk. I'm going to talk about one specific semantically smart disk system, which we call degrade. And that's a RAID system that degrades gracefully. And we'll talk about what the problem is there, what some of the design elements of this system are, some implementation things, because we've built a prototype, a software degrade, if you will, and then briefly evaluation, and then conclude this part of the talk. And again, feel free to interrupt me. I know you will at some point when I probably say something that angers you too much. So maybe I'll try to get to that sooner rather than later. So what we were thinking about in this context of building a semantically smart disk system was we started thinking about the problem of storage availability. And we all know the importance of availability, how important it is to, downtime can cost people lots of money and so forth. And the current approach that people take are some kind of RAID-based solution, which typically handles some fixed number of failures of disks well, often one, maybe two, if you're talking about row diagonal parity, for example. But some fixed number of failures well. So if we look at the graph on the right, what I'm increasing along the x-axis is the number of failures in a disk system, and what I'm showing on the y-axis is total data availability. And so if we don't have any failures, we expect to have 100% data availability. And maybe in a typical RAID, when we have one failure, we still have 100% data availability. And then after that, we have this kind of availability cliff, where we're not able to access anything anymore because we had more failures than we expected. And while that may not be a common case, it's the case that we could argue could occur periodically, or could occur once in a while even. And so what we started to wonder was, could there be a better way to behave when there are multiple failures in your disk system? And so what we wondered is, could we design a system that delivered the amount of data that it delivered was proportional to the number of disks that failed? Now that may or may not be useful depending on what your applications are that are using the storage array and so forth. But at least if most of the data was available, shouldn't we try to make it available in a sensible way to client applications? Now, in a typical storage array today, one that doesn't block-based dumb kind of storage, why these things are hard, there's a couple of reasons. There's no attention to the importance of different blocks in a file system volume. For example, one disk might contain a root inode root directory or something like that. And if that went away, then despite the fact there's all this other data available, you wouldn't be able to access it because you can't get through the top of the directory hierarchy to get to that data. There's also no attention in typical dumb storage systems to failure boundaries. Files are spread across all sorts of disks, and that means if some disks go away, a lot of files will be affected by that. And so we have to think about those issues, but it's hard for a storage system, a typical storage system, to know anything about these things because you have to know about what the file system knows. And typical storage systems don't know these things. So the solution that we're going to talk about today is what I already mentioned, is called Degrade. And this is going to utilize semantic knowledge about the file system in order to improve availability. And so it's going to try to degrade gracefully under multiple failures. It also does something which I won't talk about today. We also have some techniques in there to allow Degrade to recover more quickly from a failure by knowing which blocks are live or dead, and then only restoring blocks that are actually live and being used by the file system. And the key to operation Degrade, as you also see, is that it's okay for Degrade to be wrong once in a while. It turns out it's very hard for a block-based storage system to know exactly what's going on with the file system in a given instant, and I'll show you why that is. And it's okay for Degrade, it turns out, to be wrong about it for a while, as long as eventually it figures out what's going on exactly. And if that doesn't quite make sense, that's okay, because I'll explain it in a little more detail shortly. So back to the outline. Hopefully describe the problem that we're looking into with Degrade in a little bit more detail, which I've done. And now I'll just talk a little bit about a couple of the design issues for graceful degradation. So at the start here, we said, well, what's our goal? And our goal was to be, if the number of failures is less than or equal to whatever the threshold number of failures that our RAID strategy should be able to handle, for example, if we have parity encoding, straightforward RAID 5 kind of system, we should be able to handle one failure. A Degrade system should be just like a typical RAID system. So it should be complete availability of data at that point. What we're interested in is what happens when the number of failures goes greater than that level. So if we have 2 failures in such a RAID 5 array. And in that case, we'd like data availability to be proportional to the number of working disks, or the data loss to be proportional to the number of failures. And so what we then asked ourselves are, what techniques did we need in order to achieve this kind of graceful degradation? Okay, so the first problem that we came to, which I already hinted at earlier, is that some blocks are more important than others. So in this diagram here, we have a directory block in blue, which points to an inode, which is kind of this, on my screen it's green, but it's light green here, which points to some user data blocks in red, darker green, and lighter green. And the color code corresponds to which disk these blocks are on. So you can see the 4 disks in a storage system. Let's pretend it's just a striped storage system with no redundancy for simplicity. And the obvious problem that you're all anticipating probably now is, what if this disk goes away? Well, what happens is our directory becomes inaccessible, and even though the inode of that file is accessible, and even though the data of that file is entirely accessible, we no longer can reach that file. And so one thing we need to think about in our system is we need to make sure to replicate important blocks like metadata blocks, like directory blocks, aggressively, more than we would replicate typical user data, to make sure that any live block in the system is always reachable. So that's one technique that we're going to employ inside of Degrade. The second thing, which I also hinted at earlier, is a problem that it's kind of what we call the diffused impact of failure. So we have 4 files here, A, B, C, and D, color-coded. File A is all red, and file B blue, and then green and yellow. And in a typical RAID-style fashion, what we do is we spread these blocks across all the drives of the system. And so what you can see is the red blocks get spread across blue and green and yellow and so forth. And again, we have the same problem, where if we have a single disk, suddenly something happens to that disk. What's going to happen is 3 of those 4 files no longer are entirely available. File D was luckily unaffected because it happened to be a small file. But you can see a lot of files, especially any files of reasonable size in these types of arrays, aren't going to be available after this type of failure. Again, in this simple example, we're not doing any redundancy, but we could make the same argument for a redundant array with 1 extra failure. So what we need to think about is a different placement strategy inside of Degrade than we would inside of a typical RAID system. And so what we're going to do is what we call fault-isolated placement. And the idea here is very simple. We're just going to pay attention to those failure boundaries when we lay out data. We're going to say, put file A within 1 disk, file B within another disk. Yeah, you're going to ask for my next slide, I think. But
we've got, one of the big issues that we have is because you're bandwidth constrained by going to 1 disk, you really want to try and spread it out over a whole bunch of spindles. So how is that going to interact with this?
Yeah, I'll get to that in a second. Yeah, next slide. So Steve Rod and I go way back. So Steve's continuing what we did in grad school, which is he's still trying to give me a hard time. So I appreciate that, Steve. So we'll see that what happens here in this case, if this 1 disk goes away, yes, you lose file C, but then A, B, and D are still available. And as Steve astutely pointed out, what we have is a problem. We have these files that have now been fault isolated, so we've laid them out for a better availability, but we might lose something in performance. And so we don't have any amazing answer to this problem. But one thing that we've looked at is something that pays attention to certain hot files. Let's say there's a file that's, for example, being read a lot. Okay, that's an easier case for us. If a file's being read a lot, then what we can do is we can notice that inside the array, and then we can go ahead and make a copy of it. So there's no magic here. If you're right that there's a performance availability trade-off, and you could treat this problem in a lot of different ways. But in certain cases, it's pretty easy to imagine a replica can help you in that case. While you could still preserve the fault isolation by keeping it on 1 disk, you could also maybe keep a copy of it across the other disks and deal with some of those load balancing issues. It becomes a little harder when you're talking about things that are being written to a lot, because then clearly you have issues about which one do you want to update, how do you balance the load, and so forth. And I don't claim that we've solved all those problems, but you're right, we absolutely introduce a problem there, and this is some sense of how you might solve it. And that's the 3rd technique. So that's Degrade. Very simply, I've left some details out just for time's sake, but that's Degrade from a design perspective. And now what I'm going to talk about, and I think actually is a little bit some of the more interesting issues come up, is how do we go ahead and build this inside of a block-based storage system? So our prototype for Degrade is what we called Alexander. So why did we call it Alexander? Yeah, okay. So some of you are smiling at me, or at least frowning at me, so I know Alexander Degrade, yes. And so what we have is a semantically smart disk prototype, which works under, any semantically smart disk system has to work under a particular file system. It has to be somewhat tailored to the file system above it. There can be some mechanisms which are shared, but it has to know, oh, this is an inode, this is a directory. If it has to know those things, it has to know something about a specific file system. So we've built 2 prototypes. Most of our work under Linux ext2, though it would work fine under ext3 as well. And then another implementation under a FAT file system, an MS-DOS-like file system. Now, we didn't build this as a hardware system. We built it as a software degrade. Built it as a pseudo device driver underneath the file system. And the good side of that is it's easy to prototype that. It's pretty cheap for us to do. You can check if the thing is working as you expect it to work. And you can develop all the basic technology and I think touch on a lot of the interesting issues. But because it's not a hardware system, there's some of the performance aspects and some of the overheads, I don't think we can do realistically to really realistically understand those. And so I'll leave that as a caveat up front. Now, in building any semantically smart disk system, the one question you have to ask is, what kind of knowledge do you have to have inside the system in order to understand what the file system is doing? And there's really 2 types of knowledge. There's static and dynamic, and let me talk about those in a little more detail. Static knowledge is a type of knowledge about a file system that doesn't change during the lifetime of the file system, or if it does change, it changes very slowly, like over some period of years. For example, what constitutes the fields of an inode? how the file system, just the basic layout, what it's like, so forth and so on. And in this work, I'm just going to assume that we have that knowledge and it's embedded within our storage array. There are only so many file systems out there in the world anyway, and so if you had to embed and you wanted to support them all, you could imagine that you could embed the right information that you need across all those. We've also done some earlier work, which I won't talk about, where we actually talk about how to automatically figure out some details of those. If you make certain assumptions, it turns out you can. The main challenge, though, isn't this static information. That's information that really doesn't change in general. It's dynamic information, things that change while the file system is running on top of the storage system. For example, given a block B, which file does that block B belong to? That's important for Degrade because it wants to fault isolate all the blocks of a file, say, within a single disk. But it has to know then, for each block, which block it belongs to. And what I'll show you in this talk is that it's actually very hard to know that in the general case. And I'll show you why that is and why we can actually prove it's very hard or impossible. And then what we're going to show in Degrade is how we get around that. How do we design around that approximate or stale information about exactly what's going on in the file system and still build a working Degrade system. And so the lessons we hope to draw there are, yes, specific to Degrade, but hopefully also more general for semantically smart disk systems of this type. Okay, so I'm going to talk just about two of those techniques and how we implement them, because those are the more interesting ones. I'm going to talk about aggressive metadata replication. So we have to identify, to be able to replicate metadata, we have to be able to identify it. So that's the first challenge that would be hard for a typical dumb block-based storage system. And the second thing we're going to talk about is fault-isolated placement, which is how is a storage system going to even know which blocks belong to a given file in order to fault-isolate them, in order to put them all on, say, a single disk. Well, for some metadata blocks, it turns out to be very easy to identify them, depending on the file system that you're using, of course. On the bottom here, I've shown about the most straightforward file system you can imagine, the Linux ext2 file system layout. What you can see in white is a super block, and then in blue and then in yellow, a repeat, and there would be more of these, a set of what we would call block groups. In FFS, fast file system terminology, we would call them cylinder groups. And within each one of those units is all the stuff you need to allocate files and manage on disk space. So there's an inode bitmap, a data bitmap, inode blocks themselves, and then data blocks as well. And that repeats again. And if we just wanted to identify, for example, when a write to an inode occurs or something like that, it's very easy on this type of file system because all you have to know is this very static information. You have to know the bounds between all those regions. And so if we get a write to an inode block, we can just do a simple bounds check. That's something we call direct classification. And we can say, oh yeah, that's an inode, and maybe we want to do something special with that. Now, beyond simple metadata, things get a little bit more interesting. So for example, for directory data. Well, directory data in this type of file system lives in just the data region of the disk. And that happens to be an overloaded region of the disk. A block in that part of the disk can be a user data block. It could be a directory data block, which is a form of metadata. Or it can be an indirect pointer block, or doubly indirect, triply indirect, whatever. It could be another form of metadata. All types of metadata which we need to pay attention to inside of Degrade. And direct classification is necessary, but it's not sufficient. So, sorry. And what I'll talk to you about is it's good to know, yes, this is a data block, but we want to know more about it. We want to know what type is it right now. And so we have this technique which we call indirect classification, and that's implemented via something called inode snooping. We're going to pay attention to the inodes that get written to the disk, because those tell us a lot of information about what's going on in the system. So let me explain how that works in a little more detail. So let's say an inode gets written down to the disk inside of our disk system. We know it's an inode because we have this static information, that's an inode. And we can look inside of there. Again, we're going to assume here that we can do that we're going to have that static information. Again, it doesn't change very often. And so we can say, oh, look, this is a directory because it has a type field, has a size, and even has some pointers inside of it that are live right now. And so by looking at this inode, we can simply record in some kind of table that these three addresses, these three pointers, are directory blocks right now. Okay? And so what that means is, if we know that at that point, when, say, one of these directory blocks gets written, all we have to do is to check what kind of block it is. We can check our table here and say, does that address Is that in there? And if it does, if it is in that table, then we know this is a directory block. So that's the basic idea, and I've left out a couple details which I'll talk about that make this a little bit harder in a second. Okay, so that's how we're going to identify metadata. The one other thing we need to do, we need to identify which blocks belong to a file. And that actually ends up being a very, that was so we can implement this fault isolated placement again, so we can put all the blocks of a file within a certain, say within a single disk. The problem here is we have to track which blocks belong to which files, and the solution is actually very similar. We watch the inodes. We're going to see what blocks belong to that file, which indirect blocks, so we can look at those, which doubly indirect blocks, and so forth. And we keep track of all those things per file, so that for each file we can allocate a home site, a particular disk, or if we're doing mirroring, we could allocate 2 disks, and then put the file there and all the blocks that are headed for it. Okay. Now there's a challenge here, and there's a problem here, and there's something that makes this not as straightforward as I just described it. I'd like it to be that straightforward, but it's not, unfortunately. And the problem is that the file systems don't behave in that synchronous manner. They aren't simple. They don't tell you everything that they're doing at a given time, as you all know. In fact, they often buffer the writes that they're going to do to the disk. They delay them. Sometimes they remove them altogether. If a file gets created and then deleted, that you might not see all the traffic related to that file. And the writes might get reordered as well, depending on how the file system interacts with the I/O scheduler and so forth. So there's a lot of file system might do to basically hide, or is really trying to prevent itself from doing I/O or interacting with the disk. For obvious reasons, file systems have been built over the years assuming that disks are very slow, and that's a reasonable assumption in most cases. And so when they're asynchronous, they tend to behave a lot better from a performance standpoint. Unfortunately, for a semantically smart disk system, the result is that the information that you have inside the block-based storage system is incomplete and inaccurate. And let me tell you a little bit more why that is. So in this diagram here, what I'm showing on the top is what the file system sees actually happening in memory. So that's everything that you can imagine. That's the real state of the file system. And then on disk is what you can actually observe inside a semantically smart disk system. So let's say we create a directory called foo. And let's say that means we have an inode, and let's say that has a data block associated with it, which has directory entries in it. And let's say we even allocate some blocks for those, 3 and 5, 1 for each. And then we go ahead, and whatever reason, the file system decides to write out the directory block. So it writes it out to the disk, into this data region of the disk, let's say. And what the disk says then is, what type is that block? I know it's a data block, but I don't know if it's just user data or is it directory data, which I might want to replicate because I'm doing this degrade style stuff. So I'm going to pay attention. I'm going to see if there's anything else that's going to happen that tells me. What happens now in memory up in the file system is that foo gets deleted, so that goes away. And we create a file called bar, let's say. And let's say this is just a normal user file, which happens to have its inode allocated to the same exact block 3. And then block 5 also gets allocated not as a data block, but as an indirect block. So it's supposed to be full of pointers to other blocks that are part of this file. And then for whatever reason, the file system decides to go ahead and write out this block 3. It depends. Some file systems won't be so laissez-faire in how they interact with the disk. They might have strict orderings and so forth, but some are. Like, for example, ext2 file system will write blocks in any order to the disk. It doesn't care if your inode ends up pointing to some garbage data, so forth and so on. And that's a file system that some people do use, whether or not you think that's a good idea. We could have a debate on that at a different point, I guess. And so what the danger here is now the disk is seeing this inode being written out. And it says, oh, look, I can do my inode snooping. And I can say, oh, that file 5, block 5 must be an indirect block. It must be full of indirect pointers. I better do something with those. In fact, I better do my fault isolated placement. I better take whatever those blocks that are pointed to by that block and move them onto a certain disk. But in reality, the data in there, of course, is not indirect blocks. It's a bunch of directory entries. Though at this point, it's a bunch of bits at some point, and we could treat it inappropriately if we're not careful. So that's a problem Degrade is going to have to deal with. In particular, let's talk about with indirect blocks, how we deal with that problem. We need to identify indirect blocks, again, because we have to pay attention to which blocks a file belongs to, as I've said about 20 times now. But we can't reliably identify the type of such a block. And so our approach is just to be conservative here and eventually get it right. We're going to treat every likely indirect block and it's the pointers that it points to, like it's a real indirect block. And then we're going to copy things as we need to in that case. So if that means if there's a bunch of pointers to blocks and they say we have to move these to a certain disk, we're going to go ahead and do that. Now, we're never going to lose the data. We're going to move the data, but we're never going to lose it. So we're going to do that in a safe way. And if we later find out that the pointers are invalid, which we will, we can then take corrective action. I'm not going to prove that to you that we can find that out, but eventually you do get some signal that something was wrong there. For example, you'll find that that block, in the previous example, that indirect block may get written out at that point. And at that point, you'll say, oh, this got updated, and I have to change what I did before. Or you might see other blocks, other inodes which you know are valid, actually point to those blocks which you thought belonged to a different file. And since you know that that can't happen, you can make this kind of conclusion. And we can actually prove that as well, though I won't go through it. So the bottom line here is what we're trying to turn is this inaccuracy into a performance problem. The worst thing that's going to happen to us is we're going to move data around more than we need to, and that's something we can deal with. What we have to do then is reduce the number of times this happens. And so there's lots of things you can do to do that. One thing we do is, for example, if something comes down and we think it's an indirect block, we do some simple integrity checks that say, does this look like what an indirect block should look like? Does it have a bunch of pointers which point to different things? Or are the non-valid pointers in it all zeroed out? Because a lot of file systems do things like that. And if they don't pass those integrity checks, then we're not going to treat it like it's an indirect block. And that turns out to handle 99.99% of all cases, something like that. Okay, so that's, in a nutshell, that's degrade design and implementation. And I'm not going to spend a lot of time about evaluation because that would just take a while. So I'm just going to do one graph that shows how degrade behaves over time under failure and contrast that to a typical RAID array. Okay, so here's the graph, and it's a little complex. So I'm going to walk you through it in a little bit of detail. On the x-axis, we have time in seconds. And on the left y-axis, we have some measure of availability. So that's circled in red, and that's the percent of operations that succeed. We're doing a bunch of random file reads. On the y-axis on the right, we have circled in blue some measure of file throughput, and you can't actually read that. It says file throughput, but it's circled in blue. Okay, now we have two sets of data here. Actually, the top set, shaded in pink, if you will, is numbers for degrade. And the bottom set, which I'll shade in a very light blue, if you can see that, is for a RAID 1.0 system. So just a mirrored system that's just mirrored and striping data. And the degrade we have is also doing mirroring for all user data, as well as aggressive metadata replication and all those things we expect from degrade. And so I've also colored a couple of the lines. So the top line in each graph for degrade and for RAID 1.0 I've covered in red, and that corresponds to the left axis. So that's the availability number under these experiments, which I'll describe in a second. And then the bottom line in each, I'll shade in blue, and that's the throughput number, so kind of the file ops per second, and then I'll put on the right. And this is just a very small system. It just has 4 disks, so I don't claim this is a completely realistic setup, but it gives you a flavor of what the types of things that degrade can do. So at point 1, what we're going to introduce into the system is we're going to introduce a single disk failure, okay? And so we're going to assume we have a hot spare as well. And what you can see in both cases, the red line stays at 100% because we have a mirrored system. We can tolerate a failure, so availability isn't changed by this failure. But you can see both blue lines, the user throughput drops. And that's because, well, we have reconstruction going on. So reconstruction takes away some of the bandwidth. What you can see at point 2, though, is that degrade finishes its reconstruction more quickly. And the reason is that's part of degrade that I didn't talk about. That's the live block only recovery. Degrade knows which blocks are live or dead, and because it knows that, it can go ahead and recover only those blocks first. While the traditional RAID 1.0, which I marked at point 3, finishes sometime later. About half the blocks were live, so degrade took about half as long to get back up to normal running operation. Now, at point 4, what we do is we go ahead and introduce 2 failures. So we have 2 failures, which means some of the user data is now unavailable, okay? Which is a bad thing, and we generally don't want that to happen. But what happens if that happens? And you can see the difference in the 2 systems. In the bottom graph, you can see that the throughput and availability of the RAID 1.0 system immediately goes to essentially 0. It doesn't actually go quite to 0 because there's a few files that were cached in the host memory, and those continue to get served. It's just a random workload accessing files. But it goes to about 0, which is what we'd expect. It's a big problem. And you can see in the top, RAID in our degrade system, what you can see is availability goes to about half because we've lost one of our disks, one of our set of disks, but not the other one. And then our throughput drops a little bit because we have fewer disks. So you can see just in those 2 points with the live block recovery and then with the ability to continue operating even though we don't have all of our disks, you can see that the differences between a degrade system and a typical RAID 1.0 system. Any questions about that? People always have questions about the graph. Yeah.
You have a similar graph for, the cost of getting this extra availability in terms of space used and performance?
That's a good question. The space overheads come primarily from we're replicating all the directories in the system and some inodes that go along with that. And so what we've done is we've done a few studies of a bunch of volumes that we have access to, so academic type volumes of data. And it turns out that the space costs for even widely replicating those directories and inodes are pretty low in the few percentage points compared to the whole volume. Now that might be different if you have a different kind of volume. So the space costs actually aren't that bad because we're not replicating that much. A lot of the other work is, of course, fault isolating the data, and that doesn't change how much space overhead there is. Yeah.
Let's see if I can get, aha. But don't you actually have sort of this, I guess, metadata, right? So the file system is writing to certain blocks, and you're actually attempting to co-locate files and all of that, and so you're actually having to remap blocks.
Oh yeah, absolutely, absolutely. And
how much overhead is there for those kind of remapping things?
Absolutely. We're assuming here that like a comparison point is a RAID system that does that kind of remapping. And in that case, we're not doing anything worse than that. You're right, compared to a very simple RAID system, which does just a computation to determine where blocks go, we're paying an overhead. And that overhead isn't shown in any of these figures. We just kind of viewed that as, there have been systems for a long time, like even HP Auto RAID and going back before that understand how to do remapping in that way. And so we viewed that as a problem that we didn't have to solve. But you're right, that's absolutely an overhead that you have to pay here. And compared to a simple RAID system, it's definitely an overhead. Yeah, so I'm not including that. There you'd need, basically a pointer or two for about a pointer worth of space per block. So you can figure out that overhead as well. Okay. Yeah, sorry. Pardon me?
How do you know which are the free blocks in the system? Because file system has that information, not the...
I'll actually talk about that in a couple minutes. That's a good question. Part of a different thing that we looked at, I'll talk about. So let me just summarize degrade and then move on to the rest of the talk is actually, I have a bunch of very short snippets about some other things we did because I wanted to give a sense of the number of things we did. So I won't be spending any great detail. That was the detailed part of the talk. But again, for any part of the talk, of course, feel free to interrupt. So what we've seen with degrade is what you can get better availability in these kind of corner case situations by being more knowledgeable about the file system, by doing these certain kinds of techniques of placing data and replicating metadata. And the key, more general key to semantically smart disk systems that we found is that you always have to design around this fact that you have approximate information. You will never know exactly what the file system is doing unless it's mounted, for example, in some strange synchronous mode where it really reflects everything to the disk system. And in our case, being conservative was a technique. By assuming things were what we thought they were and acting appropriately, it was okay. We could be wrong for a while and degrade and still build a system that behaved more or less like it should. Okay. So that's the first bullet, and you should be worried again if I hadn't said already that that was the bulk of the talk. And I'm just going to shoot through the rest of these things. We've done actually a number of other semantically smart disk systems which attack different problems in this manner. And I'm just going to talk about two of them very quickly. And the second one, that secure delete one, will talk about this issue of how do you detect whether blocks are live or not. One problem that we looked at, though, before I get to that, is this multi-level caching problem that often occurs in storage systems. So you have a main host, which has an LRU cache. You have a RAID system, which has an LRU cache. And then each of those might be reasonably sizable caches. And a problem occurs, as you all might have experienced in some of your systems as well. And the problem that occurs there is when you just stack these LRU caches, they end up with a lot of redundant contents. The cache below, the RAID cache, which you paid a lot of money for, ends up having a lot of what the main host has already. And so what we wanted to think about was, could the semantic knowledge, could having a little bit more knowledge of what the file system is doing inside of a RAID array, could that help us with this caching problem? So then we started thinking about, well, what do we actually need to know in that second level cache, that cache that's sitting below the host that's in the RAID, in order to put better contents inside of it? Well, we'd like to know what's in the cache above us. And we'd like to know, so we can make sure not to cache those things in a redundant way. And we'd like to know the preferences of those cache above us, like its LRU ordering. Because we'd like to build our second level cache as, say, the next most recently used blocks, so that we're kind of extending the LRU cache across the main cache and then the second level cache as well. And these things are generally hard to know, though. Because what happens is the file system sees reads, and those reads affect which things are most recently used. So that moves that around, but it doesn't tell anything to the disk system about it. So it's hard to know the ordering. It's hard to know the contents, too, because, for example, again, when you're reading things, sometimes you read something in, you have to kick something else out. If you're kicking something out that's clean, in other words, you don't have to reflect it back to the disk, it just vanishes from the cache above you. And again, the storage system isn't informed. And so the one piece of semantic information that we took advantage of here, and again, I'm not going to go into the details of this, is that we realized that when files are read, even though we don't get any direct information about which file blocks are being read, what happens is the access time field in an inode gets updated. And then that eventually is reflected to the disk. And we found that little bit of information that says that this file has been read is an incredibly powerful window into building a model of what the cache contents above us are. It's not accurate, 100% accurate, but in a lot of cases it turns out it's pretty good. And so I'm just going to show you the results from that without talking about any further. And this is for some tiny cache examples because we have a pretty, kind of a small trace that we ran against this. But what we're increasing along the x-axis is this size of our RAID cache sitting underneath of a host cache of a given size. And what we're showing on the y-axis is the RAID cache hit rate, if you will. Again, these are pretty small caches due to the workload. And what we're showing are 4 lines. On the bottom, we see in purple there is how an LRU cache hit rate underneath that main host cache does. So you see it doesn't do that great. And what we see on the top is this red line, and what that line is labeled, it's labeled demote. Demote is something that came out of HP Labs and John Wilkes, and what that did is it explicitly changed the interface between the primary cache and the secondary cache, and it allowed the host file cache to actually control what the contents of that second level cache was. So in many senses, that was an ideal comparison point, and so we implemented it as well in our system here. And we compare against it because if you want to change the interface, that's what you do. You build demote. And what you see in the blue line, which is just above the LRU one, is a different approach that some people at Illinois or Princeton built, which is called multi-queue, which just uses not LRU in the second level cache, but some different frequency statistics and so forth to do a little better than LRU. And what you see in green, finally, is our X-ray, is what we called our system, that uses that inode field to try to build that access time update to try to build a model of what's in the first level cache. And you can see its hit rate is actually pretty good and approaches demote without changing the interface. So again, I won't talk in any more detail about that. If you have questions, we could probably talk afterwards. The last semantically smart disk system I'll talk about here is something called secure delete. And let me talk about what that is, and that's where I'll get to this liveness issue. We all know that data blocks, the contents of those data blocks often live on unless you do something explicitly. Even after a file's been deleted, data blocks might sit there. They may be recoverable. In fact, there's a whole industry about how to recover data once it's been deleted. So clearly, there's something there. You can often do it. Now, in some scenarios, that could be an undesirable thing. You might actually want that data to be deleted. And we won't talk about exactly which scenarios those are, but you can imagine they have corporate ramifications as well. And so the idea here, and it's not our idea, is when you detect that something's been deleted, go ahead and scrub the data blocks. So overwrite the data blocks of that file with some patterns of data that make sure it's very hard for that data to actually be recovered. And actually, there's been some very nice work in San Diego at the Magnetic Research Center there that shows how in a disk you actually need to do this, and how you actually have to have disks. You have to have disk level assistance to actually do off-track writes and make sure that the magnetics are such that no one can actually look at the magnetic surface and recover your data. Now, in our semantically smart disk version, the hard part then becomes is detect. If we want to do this in the semantically smart disk, we have to detect when blocks have been deleted. And I'm going to show you a little bit about how we do that. This is kind of the naive version, and I won't spend time on the more detailed aspects of it. So this is a technique that we call operation inferencing. In this case, we're trying to detect that a block got deleted. And so what we're going to pay attention to in that case, not surprisingly, are inode bitmaps. Okay, which bitmaps are still live? So let's say we see a write to an inode bitmap, and it has two blocks that are set. In other words, two inodes are live in the current version that the file system has just written out. And we can identify where that is on the disk down there. And what we can do is we can read the old version in. So we're going to read the old version in, and what we can do then is just a simple differencing operation. And what we get out of that, in this case, is with the old version had 3 live blocks. The new version that just got written out has 2, and so we can conclude that the difference in this case is this one block one inode which must have been deleted. Okay? And so in this case, the result are the files that are deleted, and then we need to go ahead and find their contents and scrub them and so forth. Now, I'm not going to talk about this in any more detail because it would take quite a long time, and it's a subject in and of itself. But with file system asynchrony and some of those problems that I showed you before, this becomes a very hard problem. And you have to be very careful in how you reason about it, because you don't want it to be that you by accident scrub things that actually didn't get deleted. You can't be wrong in this case. Well, you probably don't want that. I mean, it could be a feature, deletes all your data, whether you want it to or not, but probably not a desirable feature. And so as related to this, we've actually developed a whole way of reasoning about what a file system is doing and when can you actually feel certain that you're doing something that's correct underneath such of a file system. And so again, I won't talk about that in any detail. Okay, so that's the end. Yeah, question? Microphone, yeah.
Do these techniques work well for log-structured file systems?
That's a good question. Most of the file systems that we've been working under are, we started with simple file systems, like ext2. And simple ended up being deceiving because ext2, because it's so casual in how it updates the disk, ends up being a very hard file system to do this underneath of. As we found as we moved to more structured modern file systems, like journaling file systems, which we have quite a bit of experience with, you find that actually you have more channels of information because they're much more careful, for example, telling you what things are getting updated, so forth and so on. And so we haven't worked with log-structured file systems because we tend to work with the commodity file systems that come inside of a PC, like ext family or RiserFS, JFS, XFS, Windows NTFS, things like that. None of those are log-structured. But my guess is that there's a lot of information in a log-structured file system. When it puts something down on disk, it's doing it in a very orderly way, and you have something that you can look at and figure out what's going on. That's actually easier for us than a simple file system like ext2, which just updates blocks whenever it feels like in whatever order. So we haven't, but I think it wouldn't be that bad. Okay. So I'm going to really just talk about 2 more pieces, and I'm going to spend a couple slides on each, and then talk about our new directions in just a single slide, and then I'll wrap up. What we're doing here now is we're switching our vantage point. Now we're inside the file system, and what we're trying to do is we're trying to gather more information about, say, a RAID system that we're running on top of. So maybe we want to know more about what its chunk size is, how many disks are down there, what RAID level it's actually using. And maybe, sometimes we could know that because maybe we configured the RAID array, but maybe in general the file system just wants to learn those things. And so what we did is we developed a tool called Shear. And what that tool does is it tries to figure out those things in an automatic way for certain kinds of RAID arrays. Now, this only works on top of, I should make a few caveats here. This is only going to work on top of pretty regular, simple RAID arrays, ones that don't move blocks around all the time. So it would have a hard time, for example, if it was running on top of Degrade. But that's okay. We can do stuff like that in our world. And so I'll talk about one example of how Shear works really quickly. The first thing we wanted to discover with Shear about a RAID system that's sitting below us is what we call the pattern size. Assuming like a RAID has a repeating pattern. So if you have a stripe, for example, in a simple RAID 0, no redundancy, the size of the stripe would be the size of the pattern. RAID 5, depending on which RAID 5 layout you use, have different repeating patterns, but sometimes it's more than a stripe. But it's just how many blocks do you have to get to before you get to something that repeats? And so what we're going to do here is just develop a very simple set of simple microbenchmark that chooses a hypothetical pattern size, and we vary a bunch of them, do some reads, measure how long they take, and then use the results of that to try to determine something about the pattern size of the array that's under test. So let me show you how that works. What we're going to increase along the x-axis here is the pattern size that we thought the RAID had. And this RAID has 4 disks. It's RAID 0 and has an 8 kilobyte chunk per disk. So it has a 32K pattern size. That's what we're trying to discover, this number 32K. So we're going to start off by testing by assuming a very small pattern size. So we're going to take blocks offset at every 2 kilobytes as our candidate set of blocks. We're going to generate a bunch of reads to all those blocks that are potentially colored yellow. So we'll just pick some random subset, read them all, time it, and then we'll plot the results on this graph. And you'll see how this works shortly. We're then going to increase our offset to 4K. So we're going to only read blocks that are, of all our subset of blocks that we'll choose from, there'll be offsets at 4K in there. And so you see some blocks don't get included, but you can see all the disks still get included. So when we read some random subset of these blocks, we still get about the same time to read that random subset. And this continues for a while, and you can see the patterns change as we change the offsets that we're reading at until we get to 16K. You can see at 16K what happens is if we're reading things that are only offset, blocks that are offset at 16K boundaries, or at 16K offsets, you can see is all those line up just on 2 of the 4 disks. And so what happens is the time to read some random set of blocks from those candidate set takes twice as long. We're not using all the disks anymore. So we can observe something different happened here. And we continue, and finally at 32K, which is the right number. 32K is the size of the pattern that we're looking for here. It's the stripe size in this case. What happens in that case with a 32K offset, all the candidate blocks end up falling on a single disk. And so not surprisingly, when you try to read from all of them, that takes the longest amount of time. So we continue doing that for a while. And what we do then at the end is we have this graph, and we simply run some statistical clustering algorithms along the y-axis values. And we can see the highest cluster tells us when all the blocks happen to fall on a single disk, and that means we've discovered our actual pattern size. And again, I'm not going to go into a lot of details about this. I don't have the time. But basically, you can see how you can build these kind of micro-benchmarks if you're careful and you vary some parameters to learn something about the array that wasn't previously known to you. And you can do the same types of things to discover, like the chunk size itself, actually how many disks you have, and the RAID level itself. We have some techniques for that. Now, one thing I will hint at is how do we use this information? And what we did here is we did a very small change to the Linux disk scheduler to become stripe aware, so that whenever it has a set of blocks it wants to write out, we're going to make sure we stripe align them and write them out as a unit so we can get better performance instead of doing small RAID 5 kind of updates. This is about 20 lines of code in the very low levels of this Linux disk scheduler, a very tiny change. There's actually another fix in there. It turned out the Linux disk scheduler, when it sorted data for writing it out, in this case, it would sort it backwards and then write it out to the disk. So that was also turned out to be a non-optimal thing to do. And so we fixed that as well, but I'm not going to compare to that. And so we can see the result of this running on a RAID 5 controller, which is a very simple RAID 5 controller, is we're just writing out a bunch of files. We're changing the average file size along the x-axis, and we're showing the throughput on the y-axis. And red is the default Linux after we fix that one thing. And you can see the yellow line, which is taking stripe alignment into account, does much better than that because we're actually getting full stripe writes at that point. Okay, so how late can I go without getting anybody angry? Like 1 more minute? 3 more minutes? 1 more minute? Okay. So I'm going to skip this third part where I talk about the EMC Centara, which you may or may not be happy about. But what we did there, just briefly, is we just developed a whole bunch of techniques to actually figure out what the Centara is doing just by observing it and perturbing it and slowing packets down and slowing disk traffic down. And we figured out from nothing, we could figure out the exact internal structure of all its protocols, which I won't talk about, and a lot of its policies for how it does load balancing and so forth, and caching and so forth. And then we later verified them with EMC engineers. So you can learn a whole bunch of things, too, in these layered worlds just by being able to observe things at the right place. And then I'll end with where we're headed, which is we're headed in 2 directions right now. One way we're headed is dealing with disk failures. Modern file systems have very funny assumptions about how disks actually fail, like they work or they're not working. And it turns out, as you all know, that's not a very realistic way to view a disk. A disk can fail in all sorts of funny ways. And of course, a lot of that I learned from interacting with some people here as well. And so the first thing we did is we looked at a whole bunch of commodity Linux file systems and TFS as well, and said, how do these behave when you insert all sorts of disk failures underneath them? And it turns out they behave pretty poorly. A lot of times you can get the file systems to corrupt the file system. You can get blocks to be leaked. you can get all sorts of funny behavior if you just get a single latent sector error to occur at the wrong time. Lots of times, even things like a write failing is ignored by these file systems. They say, well, and then we even talk to developers, and that's not that developers are these bad people or these people that don't understand these things. They're like, yeah, but it was really hard to fix that problem because it turned out you have to rewrite all of how Linux interacts with the file system in order to be able to handle that problem at that point in time. And so lots of problems there that aren't being handled today, but are coming up more and more often, especially as you see Linux being run on top of fiber channel connected RAID arrays that have all sorts of different failure modes than just a single disk. One other thing that we're working on we're interested in virtual machines, which is adding yet another layer into this layered world of ours. And of course, what we need to do there is some of the same things we've been doing elsewhere, which is how do you learn about the layers above you, say the operating system, and below you, so you can get them to work better together. So it's a layered world. That's what I've been talking about. And this is our group, and which I'll conclude on. We have a bunch of students, a couple of whom have just recently graduated, one of whom is sitting right here. He's been at NetApp this summer. He hasn't graduated yet, though, but he should be. And we call our group ADSL. It's roughly for the advanced, say, systems lab or storage lab. And it's run by myself, Remzi Arpaci-Dusseau, and my wife, Andrea Arpaci-Dusseau, and we're both professors at the University of Wisconsin. So I'd be happy to take any other questions. I appreciate your patience in me running over a bit.
So, question about degrade. Have you thought about what it means to have less than 100% availability? So if you've got some subset of files available, what does that mean at the application layer? I worry about this a lot. We have systems proposed like this as well, and you can make the argument that you really have zero availability if you've got a partial availability situation.
Yeah, I think, when we first did it, we did it to push on the technology, in all fairness. We wanted to see, could we do it? And then we asked the question later, is this really a good idea? And what you're pointing out is, if some of my files are there and other ones aren't, what does that mean? If I'm running a very serious business thing on top of this, could be disaster. And it's very hard to say anything without knowing a lot about what the application itself needs. One suggestion we got at one point, and I think it's an interesting one, is would it be possible to run the RAID array in a mode where you say, okay, right now I want you to figure out what's important for me. And so you run your application of interest, and it runs for a while. And then you get some sense of what files it accesses. And then you treat that as a logical unit, which is important to you. And you either you're able to, for that application, then give all that data or none of it. And you do these kinds of techniques for that in an application-specific way. And I think, but what you're making is generally a very good point. This is done such that, it'd be more appropriate in an environment where, it's better to be able to do something. Like if you had some user directories, you could do the fault isolate placement on a directory basis, and we've done that. So some user directories are available, but not all of them. We could do something like that and fault isolate those. So you can imagine useful things like that, but you're right, in a general case, it'd be hard to say this is what everybody needs, because it could be very application specific, and applications could be structured in very arbitrary ways and touch all sorts of files. So absolutely, you're right about that.
It's like if I was sure it was a home directory, this would be great. But otherwise, yeah. I'd lose sleep about it potentially.
Yeah. Well, yeah. We work on it and then we move on to the next thing, and we don't lose sleep about
it. One more question, and so this is really neat stuff. You mentioned very early on about things like databases, and I was wondering if you've got any plans for actually extending this from just looking at file systems and inferring stuff about them to inferring information about databases.
Yeah, actually, the one student that worked on this primarily is, his name is Muthian Sivathani. He's now at Google. But before he graduated, he actually did some of the same things like degrade and the secure delete underneath some databases as well. And we actually found there it was a little bit harder to do because the data was much more structured and a little more complex than what we were getting from the file system. We did find a number of techniques that, some of the similar techniques did work, but we found it was harder for them to feel general. We also looked at things like database formats and how often they change. Remember, we're kind of assuming that those formats don't change very often for file systems, and it also turns out that database formats, just historically, people have been more willing to change them over time. So that also complicates things for us. So I think in general we found it harder. The one good news was databases all use write-ahead logging and these very well-established techniques, and a log is a great source of information. If you can peek into that log, you can see what's going on, what the database is trying to do. And if you can see that, you can take advantage of it. You don't have to guess anymore about a lot of things. So that was kind of the good news side of it. Because of the heavy logging that goes on in the database world, you really could get a lot of information from the database if you're willing to assume that you can understand the contents of the log. All done then? Okay, well, thank you very much.